Hello, my name is Teodora Bogdan and I am a research engineer at ArcelorMittal Global R&D. Today I will present you a paper related to the behavior of reduced beam sections, connections that contain heavy jumbo sections. The presentation is divided into 5 main points. The introduction, in which I would like to present you the main objective of the work, an experimental campaign on the steel moment frame connections designed using the RBS connection, the numerical procedure foreseen to calibrate and parameterize the beam and the column cross-sections, and in the end, concluding remarks. The main objective of the work is to extend the current ISC design code pre-qualification limits of such sections in matter of unit weight, beam depth, and beam flange thickness. The purpose is to cover the most range of the heavy beams provided by ArcelorMittal. The workflow has been divided into 4 steps. The first one, with the help of the design office Walter P. Moore, a multi-story frame was designed and determined the typical cross-sections needed for the beam and the columns. 4 configurations have been chosen based on the open literature availability tests and column beam weight. The second step consisted in the pre-design of the connections, taking into account the actual design code recommendations in terms of local demand on RBS and best configurations for double plates. The third step consists in the actual experimental testing of the chosen configurations. And the last one is the creation and calibration of the numerical models with the experimental campaign. The trial design is used to determine the experimental campaign dimensions, and the chosen structure is a square office tower with 15 stories tall, placed in San Francisco, a zone with high seismic accelerations. At the lower level, large steel beams were required. Many of them exceeded the current pre-qualifications for RBS. In the hereunder table, you can see the chosen beam column combinations. Specimen SP1 and SP3 had the same column sections, while the beam of SP3 is the heaviest W36 available. Specimens SP2 and SP4 aim at investigating the performance of connections made of the lightest and heaviest W44 beam section, respectively. The column sizes were chosen to have sufficient flexural and panel zone shear strength. However, it was determined from preliminary finite element models that equations for panel zone shear strength are unconservative for heavy columns with thick flanges. All the columns were designed using grade 65, equivalent of S460, while the beams were grade 50, equivalent of S355, except the beam of SP3, which was in grade 65. As said, the experimental campaign consisted in 4 beam-to-column RBS connections and were tested at Thomas M. Murray Structural Engineering Laboratory at Virginia Tech. The beams had weld access hole provided and satisfied the AWS D11 requirements. The test setup in the top right figure consisted of 4 main components: the reaction frame, the beam-to-column specimen, the actuator, and the beam lateral bracing. The reaction frame consisted of steel sections to carry the load to the reaction floor. The bolted connection between the reaction blocks and the strong floor were fully pretensioned and designed as slip critical. Load was applied at the end of the cantilever beam specimen with hydraulic actuators. The connection was subjected to a quasi-static cyclic loading based on an applied story drift. After the 0.04 radians story drift angle cycles, the displacement was increased in increments of 0.01 radians for each 2 cycles. The test continued until failure until safety became a concern. A desirable failure mode of RBS connection typically involves yielding at the reduced beam section, followed by a limited yielding of the panel zone and ultimately local flange buckling at the RBS. The latter helps in limiting the level of post-yielding hardening. Close inspection of the beam cross-sections indicates that the slenderness of both web and flanges are higher in SP2 and SP4 in comparison with SP1 and SP3, making them much more susceptible to local buckling. SP1 specimen with significantly large member size, rich flexural yielding, exhibited large overstrength and failed shortly after reaching the interstory drift due to the weld failure at the extreme tension fiber of the beam. In the case of SP2, the specimen failed by beam flexural yielding and inelastic local buckling as expected, and achieved the desired deformation capacity to pass the pre-qualification. The yielding pattern of SP2 at the end of the test can be observed in the second image. For SP3, which had significantly large member size, like SP1, yielding was mostly concentrated in the panel zone, with evident yielding observed at the double plates. As for SP2, the response of SP4 was characterized by beam flexural yielding and inelastic local buckling, while achieving the desired deformation capacity. Bending moments were assessed at the face of the column using loads recorded from actuators, whilst the short rotations theta were assessed from actuator displacement and transducer. Close inspection of the beam cross-section indicates that the slenderness of both web and flanges are higher in SP3 and SP4 in comparison with SP1 and SP3, making them much more susceptible to local buckling. To obtain a more detailed insight into the behavior, three-dimensional models beam column were constructed and analyzed using the non-linear finite element program Abacus. 8-node reduced integration brick elements were used in all models. Extruded solid elements from heavy W section representing the column were connected to the beams using tie constraints. Special attention was given to the characteristic of the RBS region and the column panel zone by considering the exact measured dimensions from the experimental specimens. The Newton-Raphson approach was adopted for the numerical integration procedure. The material properties obtained from coupons tests were considered. A plastic multilinear kinematic hardening constitutive representation was used to model the steel material properties. This was shown in previous studies to offer a reliable assessment of the monotonic and cyclic response of the steel members and connections. Although the welds were not explicitly modeled, a mesh region of half of the beam flange thickness, consisting of flange and web elements, located in the beam at the column face, were assigned nominal properties of the welding electrodes. The nonlinear numerical simulations of all four tests are illustrated in terms of bending moment, rotation curve. Comparison with the test results indicate that the analysis provides an accurate representation in terms of stiffness and yield strength, as well as overall hysteretic response. Importantly, the models can capture closely the initiation of local flange buckling, as well as development and distribution of plasticity in the RBS and panel zone regions for SP2 and SP4. Observations from the numerical models indicate that the strain maps have different inelastic distribution characteristics across connection components. The equivalent plastic strain, referred to as PEEQ in Abacus, noted here as Xi, is plotted against the short rotation. This is a scalar variable that is used to represent the material inelastic deformation. For Xi equals 0, the material is in elastic regime, whilst if it's higher than 0, indicates that the material has yielded. The equivalent plastic strain levels are analyzed at the reduced beam section RBS, at the column face in the beam flange at the region assigned with weld material properties W, in the column flanges at reaction from beam loading, CF, and at the column panel zone, PZ. The overall inelastic strain distribution varied as a function of their component characteristics. For SP1, the inelastic strain levels are similar at the weld and RBS until nearly the last cycles, while these are very low at panel zone. A particular case is that of SP3, in which the inelastic strains developed concomitantly both at the weld and RBS, only at early cycles, followed by an increase in strains at the weld and panel zone, while Xi at RBS remains relatively low, in contrast with for SP2, which developed a desirable experimental response. The plastic strain rate decreased at the weld towards the last cycles, while this is maintained or increased gradually at RBS and panel zone. On another note, the relatively high inelastic strain at panel zone, RBS, and weld for SP4 are dictated by the extensive yielding and column twisting capture in the numerical simulations. To conclude, the tested connections developed responses characterized by stable hysteretic response, a relatively strong panel zone, and reliable ductility levels. Specimen SP3, a grade 65 beam, failed in a manner similar to SP1 after completing one complete cycle of 4% story drift. Compact sections with relatively low depth to low thickness ratios may develop unreliable response, with yielding developing almost in the same time at the reduced beam section and panel zone, having a relatively equal contribution to the total connection deformation. Numerical simulations show that for connections with relatively compact sections, a higher concentration of stresses may occur at the panel zone and at the beam web, with lower stress levels developing at the RBS flanges. Thank you for your attention, and if you have any questions, don't hesitate to ask.